Hello, this is Dr. DA, and we are about to begin a new experiment. This is experiment number 5 in our lab manual, the molar volume of a gas. In class, we studied different types of laws that govern the behavior of gases, and we can bring them all together, Boyle's, Charles's, and Avogadro's, and to this one expression here, the combined gas law. As you can see it here, we discussed it in class. Of course, what it does is it says that the volume, pressure, and temperature of a gas at a particular, set of conditions can all be equal to a constant, and so it can be used to calculate, whatever value you want of any of these properties under a different set of conditions. We said that we can also collect all of these in the form of what we call the ideal gas equation. PV equals nRT, and you will remember that in this equation, P is the pressure, V is the volume, N is the number of moles, T is the temperature, and don't forget that when we are working with gases, we have to use the absolute scale of temperature. In other words, we have to go in Kelvin here. All right? In this equation, R is the so-called gas constant, and it has a value of 0.08206 liters atmospheres per mole per Kelvin. Now here's what we have to remember, that how was that value obtained? It came from data that said that the molar volume of a gas is 22.414 liters per mole. This is at STP, which we said means standard temperature and pressure. For our purposes, what that's going to mean is 0 degrees Celsius and 1 atmosphere of pressure. If we use that value and we plug it into this equation, along with the corresponding temperature and pressure, we can calculate this value of the gas constant, the 0.08206 liters atmospheres per mole per Kelvin. One of the things we're going to do in this lab is ask the question, can we reproduce this same result? That's going to be one of the things that we're going to be trying to get at in this lab. Can we reproduce this result? Okay, so to do this, we're going to do a chemical reaction that you've seen before. This is the decomposition of potassium chlorate to produce KCl and oxygen gas. And you may remember that we may have used this as one of our first equations to practice balancing equations. A couple of things we might not have mentioned at that point were the following. One of them is that the reaction requires us to put in heat in there, and the reaction also requires an extra substance. So this substance here, MnO2, we're going to call it, although it's probably not the correct the correct name according to our rules of nomenclature, but it has a common name, manganese dioxide, and it is meant to be used as what's called a catalyst. A catalyst is a substance that helps the reaction move at a faster rate without itself being consumed in the process. Okay? Now here's the thing. We are not going to be working with pure KClO3 because the reactant that we have will actually be a mixture and that mixture will have potassium chlorate and manganese dioxide. But the deal here is that this mixture, we don't know what its composition is. So you're going to be given, you're going to be given a mixture of unknown composition. And one of the goals of this experiment is to find what is the percent of potassium chlorate in that mixture. All right? Now, the other thing we're going to do in this lab is we are going to experimentally obtain certain values, certain measurements of this gas. So we're going to obtain the number of moles of gas, the volume, the temperature, and the pressure of this oxygen gas. And then what we're going to do is we are going to use the combined gas law to ask the question, if we have these values under our lab conditions, what would be the volume of 1 mole of oxygen at STP? Remember that we said that according to literature, that value should be 22.414 liters per mole. Let's see if we can get the same value here or something close to it. So to summarize, these are the two objectives of our experiment. Number one, find out what is the percent composition of our mixture. Number two, see if we can replicate the result of what is the volume of 1 mole of oxygen at STP. All right? So here's what's going to happen. You're going to receive an unknown, and what you're going to do is you're going to wait. Oops, let me get that out of there. You're going to wait an empty test tube. To which you're going to add half of the unknown sample that you receive, and then you're going to weight the test tube plus your sample. And then you're going to set up our apparatus for analyzing this reaction, okay? So your first couple of pieces of data will be the mass of the empty test tube and the mass of the test tube plus the sample, all right? What you'll do is on your data sheet, you're going to record those values right here. Here is the mass of your test tube, and here's the mass of the test tube plus your sample. The idea here is that way you make sure that your mass of the sample is accurately determined, all right? So let me show you what the apparatus is that we're going to be using here. So this is what it's going to be like, and in our second video, I'm going to walk you through how to set this up and how to run the experiment. Okay, notice here on the left side, we have a test tube that has our unknown, and that is connected to a small tube that goes into a flask that is full of water, into which is a longer tube that is connected out here to a beaker. So the way this is going to work is as follows. We're going to start heating this test tube that has your unknown mixture. As the potassium chlorate in that mixture reacts, it produces oxygen gas, which will exit the test tube through this tubing here and into the reservoir of water in the flask. Now, because matter occupies space, that means that the water in here is going to have to exit, it's going to have to be displaced, and it's going to do so through this longer tube, which is the delivery tube, and it will exit over here where we will collect it in this beaker. So this is going to be water displaced. All right? At the end of this process, we will have displaced, as you can see, a bunch of water. Oops, hold on a second. Let me come back here. So we have this displaced water here. But we're going to have to figure out a way of measuring the temperature of the oxygen that's going to be in here, inside the flask, and also its pressure. We don't have a way right now of inserting any kind of sensors in there. So here's what we're going to do. You are going to, when the reaction is finished, you are going to equalize the water levels between the beaker and the flask. You may have to, lift up the beaker or lower it, but the important thing is that when you have the levels of water equalized, the pressure inside your flask is going to be equal to the pressure on the outside. Now, the pressure on the outside is simply the pressure of air, which we're going to measure in a barometer. And I'll show you how to work that out in our demonstration of the procedures. The other thing we're going to do is we are going to measure the volume of displaced water. And again, because of the conservation of mass, we have to assume that all of the water that was displaced by the oxygen inside here, and therefore that should be the same as the volume that the oxygen gas is occupying. The other thing we'll do is we're going to take the temperature of the water in the flask, and assuming there is a sufficiently fast exchange of energy between the gas and the water, we will assume that the temperature of the water is the same as the temperature of the oxygen. So once we have the temperature of the oxygen, the volume of oxygen, we'll also have to adjust the pressure of air that we measure to obtain the actual pressure of the oxygen. So I will explain that later on. So again, we'll have the pressure of oxygen, we'll have the volume of oxygen, the temperature of oxygen, and of course, the question would be, how are we going to get the number of moles of oxygen? And the answer is, we are going to use the stoichiometry of the reaction to find that. Oops. I have a keyboard showing up in here for some reason. Oh, here you go. I got it. We're going to use the stoichiometry of the reaction to deal with that. Okay? So let's go back to our procedures here. What's going to be important is that once we have run the reaction, let me zoom out of here a little bit so we can remember where we were. We are going to weight the test tube plus the product. Now remember, when we looked at the equation here, remember that we started out with potassium chlorate. Of that initial mass, some of it became oxygen, some of it became KCl. So that means that since the oxygen was essentially removed from the test tube, all that is left is KCl. Therefore, the resulting mass should be smaller than what we started with. However, we want to make sure that that has finished reacting, and so what we're going to do is we are going to do another cycle of this. In other words, we're going to reheat the test tube plus the product. Okay, we're going to do this. We don't have to reassemble the apparatus. We're going to be just an open test tube. And then we're going to reweight. And that'll give us another mass here. All right. And the goal is for masses 3 and 4 be no more than 10 milligrams different. That is a way of assuring ourselves that all of the potassium chlorate reacted. And I don't know if you remember this, this is what is called heating to constant mass. Okay? Now, on your data sheet, these values are going to be recorded here. This will be your mass of your product in the test tube. And then after the second round of heating, you'll have that in there. Now, if after that second round, it turns out that the difference between those two items was more than 10 milligrams, then you'll be asked to do a third cycle here, again with the open test tube. And the goal is to find the difference to be no more than 10 milligrams. Don't forget that you will also have to be recording the pressure of the atmosphere on the barometer, the temperature of the water, and the volume of water displaced during the process. Okay? So, in our next video, we're going to walk you through how to set up the apparatus, how to equilibrate the pressure, how to carry out the reaction, and then we will do a third video where we'll walk you through the calculations so we can answer the two questions of this lab, which are, number one, what is the percent of potassium chlorate in our mixture? And number two, can we reproduce this result for the volume of 1 mole of oxygen at STP? Thank you so much, and we'll see you later.